Hello everyone, welcome to the world of point-and engineering. In this video we are going to discuss about our tutorial number 3, or you can say that experiment number 3, which is about the design and simulation of dipole antenna operating at 1 GHz using CST Studio. So let's begin. First of all, start your CST Studio and create a new template. So just click on microwave and RF and optical, and as you have to design an antenna, so click on antenna and just click on next. As dipole and monopole antennas are wire antennas, so that's why you have to select wire antennas and just click on next. As we have already discussed that time domain and frequency domain are the most common solver in CST, so you can select time domain or frequency domain solver for designing such type of antennas. These are the different parameters of different values, so I think no need to change the parameters, and just click on next. Now you have to define the frequency, as we have seen in title that our antenna operates at 1 GHz, so let's define the frequency from 0 to 2 GHz. Okay, so as far as the values of monitor is concerned, E field, H field and far field results will be required, so that's why just click on E field, H field and far field. And similarly our central frequency will be 1 GHz, as you have defined that our antenna will work for 1 GHz frequencies. So after defining all these parameters, review your basic settings, basic values, and then just click on finish. So your project will be started. So now move towards the manual. So there are two methods in this manual that I have mentioned. First method is that you can design both of the poles, or you can say dipoles, separately. Okay, and the second method is that first of all you have to simply define a single cylinder, and then you can cut a part between the center, or you can say that inside the center of a larger cylinder. And after cutting that part in the center of larger cylinder, you will obviously get two cylinders or two poles, which will also be considered as a dipole. So first of all, let's begin the method number 1, which is very simple, and you can learn the simple concept of designing poles in CST. So first of all, you have to go to the modeling, and then you have to define the cylinder, and you will use obviously circular cylinder. Okay, and then you can press the escape key, or you can draw the cylinders on different points as well. So first of all, go to the modeling, and then you have to define the circular cylinder. So just click on circular cylinder. Now you can define the cylinder on different points, or you can say that by defining different points, but you can define the values in a dialog box as well, like you can say that the name of this first cylinder is dipole 1. Okay, so now you can change the values in this dialog box. For example, if you want to design the monopoles, or you can say that design the poles in Y direction, then just click on Y. Okay, and then you have to define all these values. For example, what will be the value of radius of the cylinder, and what will be the value of the length of the cylinder. So all these parameters are directly associated with the calculated values from the formulas as per the defined frequencies. So if you have any doubt about the values of outer radius, or you can say that if you have any doubt about the length of an antenna, so the basic concept of defining the value of outer radius as well as the length of the pole. We have already discussed its basic concept in previous video as well in our tutorial number 2. So I will mention the link in the description of previous video, and you can check the values and basic concepts and formulas, that how you can find the value of outer radius, how you can find the length as per the formulas for different operating frequencies. So these values are calculated for the frequency of 1 gigahertz, right? So we have already calculated these values of outer radius and the length of the dipole. So just define the values as mentioned in this manual. So outer radius will be 2.5, and similarly you have to design this antenna on X and Y center at origin position, at the position of origin. So X center and Z center will be 0 0. Now along the Y axis, as we have already defined that you want to design that pole along the Y axis direction. So now along the Y axis direction you have to define the length of that pole. So the length of the pole is starting from 10 to 49.45. So just define the value here. Y min will be 10 and Y max will be 10 plus 49.5. So 49.5 will be the total length of this dipole, or 49.45 will be the total length of this dipole. However, this dipole is basically starting from 10 millimeters, right? So now you have to define the material of this dipole as well, and you can use the material as a copper anneal. Okay, so just press the C, and then you can easily define the material as a copper annealed. Okay, so just click on preview, and now you can check its preview that your first pole is along the Y axis, whose length is about 49.45, and that is basically starting from 10 to 49.45. okay, so just press OK. So that is your first pole. Okay, so similarly as you have to design the dipole antenna, so you have to define another pole in same alignment. So again you have to put the similar values, so that will be dipole port part 2. So again go to the modeling and select circular cylinder, and then you have to define the values. So these similar values, outer radius will be same, and as alignment will be same, so X center and Y center will be 0 0. Now you have to define the length of this pole along the minus 10 to minus 49.45. okay, so by defining this value minus 10, it means that you have to define the gap of 20 millimeters between these two poles. So that's why we have started this pole from 10 and the next pole from minus 10. All right, so that's why we are using such type of values. Same material will be used. So just go to the modeling, click on cylinder, and now you have to define that cylinder along Y axis. Okay, you can simply press the escape key. However, you can define the values as well. So that will be dipole part 2, right? So now you have to define the radius. As you know that first of all you have to define this dipole along the proper alignment, or you can say that you have to define the dipole along Y axis. So that's why I just click on Y. Now define the radius. Radius will be same, so outer radius will be 2.5. X center and Z center will be 0 0, as you have to define the dipole along this center. So now you have to define the values. Values will be minus 10, and from minus 10 to 49.45. okay, so material will be copper anode. So just click on preview. Now you can check that this dipole is along the same alignment with similar radius. Okay, so just click on OK. So your dipole is almost ready, and the distance between these two poles is about 20 millimeters, right? So now move toward the next step, and that step is basically defining, or you can say that defining the excitation port for this dipole. However, let's discuss about the method 2. You can use the method 2 as well. It is again a very simple procedure. First of all, you have to define a larger cylinder instead of defining two separate cylinders, right? So from as you have observed that this cylinder was starting from -10 to -10 to 49.45. so the total distance, or you can say that the total distance from the origin was -59.45. Similarly, the total distance along the positive axis was plus 59.45. So by defining the overall values of 59.5 and minus 59.5 with a similar outer radius and similar material, you can define a single larger cylinder. And after defining single larger cylinder, you can define a smaller cylinder with different material of nickel with similar radius, but as you have to define the gap of 20 meters in the center of larger cylinder, so that's why you will define its values of Z mean and Z max from -10 to +10. And then after defining this cylinder, as this cylinder has different material and both the material are rigid material, or you can say that both are metals, so that cannot be placed in a similar places. So that's why when you click on OK after defining this cylinder, you will receive a dialog box, or you will receive a notification in terms of a dialog box, and in that dialog box you have different options, and the last option is that you can cut away the highlighted shape. So by selecting this last option, you can remove the central part, and you will get the dipole by using method 2. Okay, similarly, instead of cutting it away, similarly you can subtract the larger subtract the smaller cylinder from the larger one as well, right? So from modeling and by subtracting smaller cylinder from larger cylinder, you can perform the same task as well. So these are the two different methods, and I think you got the point that how you can define the dipole by using different methods. Okay, so after defining the dipole, now you have to define the wave port excitation, and for that purpose you have to select the 2 points that between those 2 points you can define your discrete port. So it will be better if you select the 2 points and then you will define the discrete port. Otherwise you can define the discrete port, and then by putting the values of all the points you can easily define the discrete port, like these points x1, y1 and z1, and similarly x2, y2 and z2, but it will be difficult to calculate the exact central positions in case of complex antennas. So it will be better if you select the central position of both the cylinders and then to define the discrete port. So first of all, you can just define the central points from modeling as well as simulation. So first of all, just zoom in the cylinder, and then you can define its define the point at its central position. So just click on modeling and just go to the pick, and then you can pick a point by simply clicking on pick points, and then you have to select pick circle center. You can use a shortcut command of C as well, right? So that's how you can define the central point. So that is central point number 1 on dipole part 1. Similarly, you have to define another point on second dipole. So just go to the modeling, click on pick points and select pick circle center. So just okay, now you can observe that this is P2 or point 2 and point on the other part is basically point 1, P1. Okay, so as we have already defined the 2 points, and now you can define the discrete port between these 2 points. So just go to the simulation and just click on discrete port. Now you can see that a proper discrete port has been defined between these 2 points. Okay, so x1, y1, z1 and the values of x2, y2 and z2 have been already defined by using these pick points. Okay, so input impedance is 50 ohms, so just apply and just click on OK. So that was the complete design procedure of dipole antenna. Now go to the simulation and just define the field monitor, but before starting the design we have already defined the values of field monitors as well, E field, H field and far fields. So we have already defined the frequency as well from 0 to 2 gigahertz. So all the parameters have been already defined. So just go to the home and just click on start simulation. So this simulation will take some time, and after the successful completion of simulation we will check the results of S parameter and its gain. Okay, so simulation has been completed. Now you have to check the results of this dipole antenna. So to check the S11 or S parameters of this antenna, you have to just click on 1D results and then just click on S parameters, and you can easily check the values of S11 from this graph. So you can observe that this antenna basically operates at 0.95 gigahertz, and it is just because of using calculated values. As in the start of video I told you that we have basically used the calculated values from the formulas, and that formulas were discussed in tutorial number 2. So mostly calculated values does not provide us exact dip at the defined frequency. However, you can optimize the results as well. So in that case you can check that this antenna will work for 1 gigahertz as well, because antennas with the value of S parameter less than -10 dBs can easily use for any purpose, and the value of S parameter at 1 gigahertz is -11.78. so it can work for 1 gigahertz. However, you can optimize the results of this antenna. Now the question arises here is that how can you optimize the results of this antenna, specifically the S parameters of this antenna? As you know that the size of antenna is inversely proportional to its operating frequency. So if you want to increase the frequency of this antenna, obviously you have to reduce the size of antenna, and in that case, in case of dipole antenna, size means that you have to reduce the length of dipole. So simply by reducing the length of dipole you can easily shift the frequency to the 1 gigahertz. So in this way you can optimize the results of S parameter as well. Okay, similarly if you want to check the results of its gain and radiation pattern, then just click on far field and then far field at 1 gigahertz, and now you can check the results of gain and as parameters. So first of all, it provides the gain of 2.16 dB, and you can check that monopole and dipole antennas mostly radiates in all the directions, or you can say that somehow it provides omnidirectional pattern. So that is basically omnidirectional pattern of this dipole antenna. Similarly, if you want to check the results of radiation pattern at E and H field, then you can just change the cut angle to check its radiation pattern at E field, as well as radiation pattern for H field. Okay, so in this way you can design a dipole antenna, and you can check the results of dipole antenna after successful simulation. So thanks for watching. Subscribe One Time Engineering for latest videos, and press the bell icon for latest videos notifications. Thank you so much.